Hi there. So I'm going to do a brief introductory video to a mathematical tool called trigonometry. Um, so trigonometry is to do with triangles, and at the most basic level is to do with right angled triangles. So we'll start with some definitions. I'll just draw an arbitrary right angled triangle. Um, so the side opposite the right angle is known as the hypotenuse, and that's always the longest side of the triangle. That should be fairly intuitive, but you could think about supposing it wasn't the longest, and then seeing what problems would arise if it wasn't, and you can kind of prove to yourself that it must be the longest side. And then let's say we know this angle here, then this side we can call the adjacent. That makes sense, right? Because it's next to the angle. And we can call this side the opposite. It's opposite the angle. This makes sense. Okay, so we'll call this angle theta. You may be used to the variable x. Theta. Theta's a Greek letter. Like, so you may be used to x as a variable when you're solving equations, for instance. But as angles, we tend to use theta, just out of convention. So I'm going to define some functions as well, the functions of trigonometry, if you like. So we have sine of theta. Don't worry if you this seems a bit random at first. It will make sense later, I promise. So sine theta is opposite over hypotenuse. I'm doing this as abbreviated notation for opposite. Hypotenuse should be fairly obvious. We're going to define cosine theta as equal to the adjacent divided the hypotenuse. These are lengths, by the way, so like the length of the hypotenuse, the length of the opposite, etc. And this is just a function. I'll explain that a bit more in a minute. And tan theta is equal to opposite over adjacent. Okay, so what this means is, say we have I don't know, the opposite side and the hypotenuse, the lengths, then we can say that sine theta is the ratio of this, and so we can do, in that case, the inverse function and get that theta is inverse sine of opposite over hypotenuse. So you have to use your calculator for this, but I'll give you an example, so it'll hopefully make a little bit more sense. So say we have this right triangle with side lengths 3, 4, and 5. If any of you are aware of Pythagoras' theorem, then it might make some sense why I've chosen 3, 4, and 5, known as a Pythagorean triple. If you're not aware, then I'd recommend you look it up. I'm making a really poor mess of that 4. There we go, that's a 4. And we want to know, let's say, this angle here. Then recall that sine theta is equal to opposite over hypotenuse. And so with this triangle, we can say that sine of theta is equal to, well, this is the opposite side, right? So this is 4 divided by the hypotenuse is 5. Okay, and if you've done functions, then hopefully this should make more sense. But even if you've not, then it should make some sense. Basically, we can do the opposite. We can kind of undo this sine by applying inverse sine to both sides. And we can say that theta is equal to sine to the minus 1 of 4 over 5. Which, when you immediately look at that, it doesn't really make a ton of sense, right? But we can use our calculator and say shift sine, might not be shift, depends what calculator you've got, 4 over 5 is equal to 53 point, okay, loads of decimals, degrees. So that means that this angle is approximately 53.1 degrees, so I write that. So theta, I'm making a really poor job of letters today. Theta is approximately 53.1 degrees. So that's cool, right? I mean, you can say, given any sides, well, you need two sides of the triangle, and you need to know it's a right angle triangle, and then you can say what these angles are. And similarly, we could have done this other angle. So let's say this one. We'll call this angle alpha. It's another Greek letter, and we can say that sine of alpha is equal to, again, the opposite over the hypotenuse. So in this case, 3/5. And again, applying the inverse, we can say that alpha is equal to sine to the -1 of 3/5. So using our calculator, we see that that comes out as 36.9 approximately. So alpha is approximately equal to 36.9 degrees. And for those of you who are aware, hopefully most of you are, that the sum of the degrees, the sum of the angles of a triangle should be 180 degrees. We can kind of check that this makes sense by saying that we're considering the sum of the angles. So we can say, okay, the sum of the angles is 90 plus 53.1 plus 36.9, which, hope you see, is 180 degrees, which is kind of a good check. That makes us feel nice and warm inside. And the final way of using these functions for right angle triangles is by using a different rearrangement. So I'll take you back briefly to the initial definitions. We can rearrange any one of these. So say, for instance, this top one, we can say that the hypotenuse multiplied by sine theta is equal to the opposite. So I'll give you an example of using that. Let's draw this one a bit differently. Again, it doesn't matter any right angle triangle, no matter how it looks, no matter what the kind of orientation. This is always going to work. Let's say we have this angle here is 30 degrees, and this side here is I don't know, length 4, let's say. And given these two pieces of information, we can now work out either this side or this side. So this is the hypotenuse, remember, the side opposite the right angle. And given the angles here, this is now the opposite side. Okay, you remember the opposite and the adjacent are defined depending on which angle you know, not the right angle, but the other angle, either the one you're trying to find out or the one that you know. So this time we'll work out the opposite first. So the way to do this is to think what piece of information you have. So you know you've got this angle, and this 4 represents the adjacent. I'll put it in brackets. This is like the adjacent. And we want to find out the opposite. Okay, so there's a neat way to remember the formulae at the start. So sine theta is opposite over hypotenuse, so we can write that as, let me just change colour, so, like that. Sine theta opposite over hypotenuse. And then cosine theta is equal to the adjacent over the hypotenuse. And tan theta is equal to the opposite divided by the adjacent. And so we've got a nice little soccer toa going on there. So that's a nice way to remember it, I guess. So looking back at this example, if we want to find the opposite, when we've got the adjacent, then we look at the one of these which has both the opposite and the adjacent in it, and we see that it's this one. And writing that out properly, that's tan theta equals opposite over adjacent. Rearranging this gives adjacent multiplied by tan of theta is equal to the opposite. And so now we can substitute in the values that we know. So we know that the adjacent is 4 multiplied by, okay, this is just the angle, so tan of 30 degrees is equal to the opposite. So again, break out the old calculator. So 4 tan 30 is equal to, okay, 4 root 3 over 3, which as a decimal is about 2.3. So I'll just approximately 2.3. So that means that this Okay, I've drawn it slightly wrong. If you realise, that's not really a 30-degree angle, right? That's more of a 60-degree angle. So that's why it doesn't really make sense with the diagram. Maybe a better effort at the triangle would look something like this. Yeah, no, that looks more like 30 degrees, sorry. And so it says that this length here is 2.3. So if we were working in centimeters, and this was let me write that 4 again. And this was 4 centimeters, then this would be 2.3 centimeters. And we can do the same with the hypotenuse, using either of these two now, given we know that. And we can work out all the sides and all the angles in the triangle, as long as we know that it's right angled, and then 2 other pieces of information, whether it's 2 side lengths, an angle and a side, whichever of the sides, then we have enough information to work out all the other lengths that we'd want to know. Okay, I hope that was useful. Please look up trig, it's really cool, and it applies to more than just right angled triangles, but I hope you enjoyed that. Thank you.